In the cloud, the term database is just too narrow to describe the depth and breadth of options for the various ways in which data can be stored, manipulated, used, and shared. And in this session, you'll get comfortable with two nearly interchangeable terms, data services and data resources, and learn about the primary Azure data resources. When you listen to the word database, you already have some images in your head, and they typically involve relational data. Possibly for you, the symbol for architectural diagrams and other documentation related to data looks something like this. And inside, the data format consists of predefined columns or fields and interconnecting tables. The data itself is represented in rows and columns that look like this. And you get to those rows and columns with a query written in SQL structured query language. And then you pass along either that query or the results of that query to a person or feed it into a tool which produces pretty pictures like these, which are called visualizations that provide insights into making business decisions. The infrastructure and services that are hosted in the Azure cloud are called resources. Relational data resources in Azure include SQL Server on an Azure VM, which is pretty much less like a traditional SQL Server database in an on-prem data center, but the VM or virtual machine is hosted in the cloud. The cornerstone of relational resources in Azure is Azure SQL Database, which is based on SQL Server and is available in multiple configurations. In addition to Azure SQL Database, Azure offers three open-source relational databases: Azure Database for MySQL, Azure Database for MariaDB, and Azure Database for PostgreSQL. Azure Synapse Analytics is Azure's modern data warehousing offering. Under the covers, it's also a relational database, but you won't see that in the Microsoft documentation. Non-relational data resources, which are sometimes referred to as NoSQL, may still be represented generically. You connect to a database like this, as non-relational data is more likely to be cloud native, versus on-premises. The data is flexible and semi-structured in documents that may look something like this, or in the form of interconnected nodes with the focus on the relationship between the nodes like this, or even in tables which look an awful lot like relational data, except you might notice that there are different columns for each row. This enables something called schema on read. Finally, we have unstructured data, which can take virtually any form but is usually characterized by document types such as images, videos, PDFs with a mix of textual data and image data, and other unstructured textual data. Nonetheless, many of these resources can be queried using the same SQL or SQL-like queries used for relational data. And also, like relational data, you can pass the results of the query onto a person or feed it into a tool, which produces those same pretty pictures and provides insights into making business decisions. Non-relational data resources that will be focused on for this course include Cosmos DB and its many interfaces into various non-relational data formats, and Azure Storage Accounts, which encompass Azure Table Storage, Azure Blob Storage, and others that we'll talk about in other lessons. Data is a collection of facts such as numbers, descriptions, and observations used to record information. Data structures in which this data is organized often represents entities that are important to an organization, such as customers, products, sales orders, and so on. Each entity typically has one or more attributes or characteristics. For example, a customer might have a name, an address, a phone number, and so on. You can classify data as structured, semi-structured, or unstructured. Structured data is data that adheres to a fixed schema. So all of that data has the same fields or properties. Most commonly, the schema for structured data entities is tabular. In other words, the data is represented in one or more tables that consist of rows to represent each instance of a data entity and columns to represent attributes of that entity. Semi-structured data is information that has some structure but which allows for some variation between entity instances. For example, while most customers may have an email address, some might have multiple email addresses and some might have none at all. One common format for semi-structured data is JavaScript Object Notation, or JSON. Unstructured data is known as blobs, which can be anything, but are most commonly associated with images and videos. However, they can be represented in other formats such as PDF and Microsoft Office documents. Now let's look at some formats of storing data. The first one is JSON, that stands for JavaScript Object Notation, and is the most common data serialization language that is commonly used for transmitting data in web applications, but it can be used for a variety of other applications as well. Next, we have YAML. YAML stands for Yet Another Markup Language. YAML is a strict superset of JSON, another data serialization language. But because it's a strict superset, it can do everything that JSON can and more. Additionally, JSON can transform into YAML as well. YAML itself can also contain JSON in its configuration files. YAML uses indentation to define structured data. Finally, we have XML. XML stands for Extensible Markup Language and is, like the name suggests, a markup language unlike JSON or YAML. It can also be used for storing data or configurations in a structured format. XML uses a tag to define the structure just like HTML, as you can see here. In this session, you'll become familiar, at least at a high level, with the data languages used to interact with data resources in Azure. So let's get started. Here you can see a table with some user ID, movie name, genre, and audience type, and then we have a SQL query over that data resource. This first row, select star, determines which columns we want to return from our inquiry. Star indicates that we want all the columns. The second row is the database object that we want to pull that data from. Now you might remember that relational databases have tables, and often a query would be on multiple tables that are sewn together. You can also store a query as a virtual table or a view, and that view can be treated just like a table. So for right now, the only thing you really need to understand about a view is that it is a projection of multiple tables, but looks and feels like a table when you query it. So we're going to select all the columns from a view called Family Movie, where the movie name column is equal to Black Panthers. If we execute that query, it will return this single row from that view or virtual table. Here is a query over that same database object using Python. This first line of the Python is connecting to the SQLite module, and then the rest of it is connecting to the database. And then you'll notice that the select star from Family Movie, where movie underscore name is equals to Black Panthers, is identical to the query previously. So even though this is wrapped up in Python, it's actually still just executing a SQL query. Similarly, when we look at this PowerShell command that's invoked from a command line terminal, we're invoking SQLcmd, which is saying which module of PowerShell we want to apply in order to execute SQL. And then you'll notice that the query, again, it's identical. Select star from WW underscore family movie, where movie underscore name is equals to Black Panther. And then instead of representing the server connection at the beginning, it's added to the end. But essentially you can see that both PowerShell and Python at their core are simply executing SQL queries. Next, we're going to look at how we might query this JSON document. Not surprisingly, I'm going to show you how to query it with SQL. SQL is the core way that you interact with JSON documents in Cosmos DB. So we're going to bring up that same SQL query and just make a few adjustments to it. The first one is a change to the object name. There isn't a concept of views in a document database, and so rather than pulling the data from a view, we're going to pull the data from a container called movies, and that container has multiple movie documents. Those documents have all of the same data that were found in the relational table. The other change that we're going to make here is, unlike the relational query that we wrote previously, once we wrote from the views or from movies, then the system knew that that was the container or the table that we wanted. In this case, we have to explicitly state that. These are just small nuances that are different when you apply the SQL language over different kinds of resources, but it's pretty much the same query. When it comes to databases that are supported in Cosmos DB, such as MongoDB, Gremlin, which is a graph database, and Cassandra, we're going to rely on the application program interface or the API to tell us how we need to query those databases. Often it will replicate the languages that are supported by those native databases. In this case, I just want to show you how most of these languages are still human readable, even if you aren't familiar with the specifics of the syntax for that language. In this case, we're going to go into the database, we're going to go into movies, and we're going to find an object based on the fact that the movie name is Black Panthers. So I think you can look at that and decipher what the purpose of that query is and what it's going to return once you execute the query. Let's see how we can manage our data resources in Azure. We first provision, then we deploy and secure, and finally, on an ongoing basis, we manage the process. In our provisioning step, we set up a resource group. The resource group is a container for the services or resources that we're about to set up. We scope those out, we provision the services, and then we define our data level resources, or plan what we're going to put on those services. If you think about an Azure SQL database, you first set up an Azure SQL database server. That's your infrastructure that goes behind the databases that you're going to set up. So we provision the servers and then we deploy databases, we secure those assets, and then we course correct as we go. Finally, on an ongoing basis, we manage the process, or we still react to events and process the data. There are two kinds of data processing, batch and streaming. In the batch processing, data is collected in a group, whereas in stream processing, the data is collected in real time or nearly real time, or even in micro batches. So a micro batch is not a subset of batch processing. It's actually a subset of streaming because those micro batches are collected in very short time frames, usually a few seconds to a few minutes. But anything more than a few minutes would more accurately be considered batch processing. Batch processing is conducted when it's cheap and convenient. Batch processing often takes place after hours. In the case of streaming though, we want to have low latency. Latency describes the time between when the data is produced or arrives at your doorstep and when it's passed in for processing. And that's typically measured in milliseconds. So while we wait for some data and process it when it's convenient, stream processing is appropriate for data that we want as quickly as possible. Typically, batch processing follows the pattern of extract the data, transform it into the form that you want it, and then load it into your final destination. This is called ETL, or extract, transform, and load. In the case of streaming, we swap those steps around a little bit, and instead of ETL, we do ELT, and that's because of the latency being measured in milliseconds. We want to load it as quickly as possible and worry about transforming it later. So we extract it, we load it into our final destination, and then the data is transformed at that destination. Because batch data is loaded into giant piles of data, if we have dirty or corrupt data, sometimes that can impact job success. Unless we make sure that we accommodate that explicitly, and part of that is because the second step in the process is the transform step. On the other hand, streaming is more tolerant of non-conformant or dirty data because we simply extract it and load it, and then we worry about the transformation of that data later. Batch data is good for deep analysis and instances where you need lots of historical data. Analytics over streaming, on the other hand, can typically only happen over fairly recent data, usually measured in minutes or hours at the most. There are cases where data can be streamed in and used and analyzed for one purpose, and then after it's stored, it goes through batch processing for deeper analytics. There are two important terms in the realm of data processing. The first one is pipeline. Pipeline is a loaded word in the cloud. Practically everything can be a pipeline. I just want to emphasize that throughout this course, when we use the term pipeline, we're talking about an orchestrator for data processing. The second term is big data. Big data is generally characterized by the velocity, the speed at which it arrives at your doorstep, the volume, which is generally big, and the variety, all the different kinds of data that you might deal with in your environment. That defines that set of data as big data, and you want to use big data processes to manage that data. Now that can be batch. There are big data batch processes, and there are also big data streaming processes. Data engineering is the process of designing and building systems that let people collect and analyze raw data from multiple sources and formats. These systems empower people to find practical applications of data, which businesses can use to thrive. So why is data engineering, or data engineers in general, so sought after? There's more data than ever before, and data is growing faster than ever before. 90% of the data that exists today has been created in the last 2 years. Data is more valuable to companies, and across more business functions, sales, marketing, finance, and other areas of the business are using data to be more innovative and more effective. The technologies used for data are more complex. Most companies today create data in many systems and use a range of different technologies for their data, including relational databases, Hadoop, and NoSQL. Companies are finding more ways to benefit from data. They use data to understand the current state of the business, predict the future, model their customers, prevent threats, and create new kinds of products. Data engineering is the linchpin in all these activities. As data becomes more complex, this role will continue to grow in importance. And as the demands for data increase, data engineering will become even more critical. What is the job of a data engineer? To understand that, you need to know the process, which initially starts from a software engineer that develops a web, mobile app, or an IoT device. For that, they need to collect some kind of data. That's where a data engineer comes in. Data engineering is a skill that is increasing in demand. Data engineers are the people who design the system that unifies data and can help you navigate it. It finds all of the different data sets around the business, cleans the data, which is basically finding and fixing any errors in the data, like removes duplicates, and also interprets data in multiple ways. It then gives a common format. After wrangling data, it is given to a data scientist to model and train the data in order to serve a model and also visualize the data in the form of reports and dashboards to get a clear picture of the model results. Once this is done, data may be stored in a central repository such as a data lake or data lakehouse. Data engineers may also copy and move subsets of data into a data warehouse. A data engineer must be an expert in several areas, such as foundations, development environments, organization specifics, interpersonal skills, and emerging technologies. Let's look at the details of some of the skills that tell you a little bit more about the complexities of a data engineer's job. Let's look at the programming languages. At a minimum, a sound working knowledge of Python is required, but usually a master of Java, Scala, Presto, Hive, R, or any number of other languages can necessarily do the job, depending on which part of the data pipeline is involved. In an ideal world, the data engineer would be working alongside a data scientist, making sure that their code is reusable and machine learning friendly at scale. Let's take a look at database management now. Extensive knowledge of database languages and tools is required to perform data engineering. Data engineers must ensure that different databases are available to all users and functions. SQL and NoSQL are required skills here, along with advanced DBMS knowledge and skills. Analytics and business intelligence tools are a big part of data engineering. One would think that this is the realm of the data scientists, but it is more, for the most part, data engineers. However, a data engineer must build a pipeline that supports data analysis and machine learning, so it helps to understand the terminology and outputs of the end users. Data engineers also need to use statistical modeling on the job, for example, to measure the usage rate of data in a database. A data engineer really needs to understand the difference between cloud and on-premises. Companies and their external data suppliers have data stored in various cloud systems and on-premises as well. A data engineer has to bring all these databases together to enable everyone in the company to use this data. A solid knowledge of operating systems is also required. Since operating systems make a pipeline work, a data engineer must know the ins and the outs of different networks, virtual machines, server management, Linux, Unix-based systems, Windows, and much more. Now we come to containers. Containers are lightweight versions of traditional virtual machines that make it easy and less costly for teams to deploy, manage, and scale distributed applications. They provide many advantages for data scientists. The rapid rise of containerized applications is a good example of how the nature of a data engineer's job is constantly evolving with new skill sets required. A data engineer is also expected to possess domain and business expertise. In most organizations, there is a tremendous amount of legacy business information contained in the company data. Without that domain knowledge, subtleties in the data are often missed, leading to data quality issues. Additionally, without domain and business expertise, it's difficult to imagine the work of the data engineer aligning very well with the strategy of the business. Now let's take a look at optimization. The key skill here is not just to be able to build a data pipeline, but to build one that is scalable and efficient. Higher level skills are needed to design and build a data warehouse that can optimize the performance of queries, and when the data warehouse becomes very large, find new ways of making analyses perform. Data governance and security is a big issue and a major concern for data engineers. While data engineers are not typically responsible for data governance, they must ensure systems are in place for data access and user control. They need to be aware of data governance concepts and be sure that any tools and platforms they put in place support proper data governance. A data engineer needs to be creative. Clearly, data engineers are expected to have a wide array of technical expertise. Like data science, however, the job also requires critical thinking and the ability to solve problems creatively. This might include creating solutions that don't yet exist. Collaboration is key for data engineers. In addition, data engineers must also be able to work effectively in collaboration with other data experts and communicate results and recommendations to colleagues without technical backgrounds. Most problems with big data are people and team issues. They are not technical issues, at least not in the beginning. Technology usually gets blamed because it's far easier to blame the technology than to look inwards at the team itself. Until you solve your personnel issues, you won't hit the really tough technical issues or create the value with big data that you set out to create. DevOps. There is a skill set and mindset that comes with being in an ops role, and it can be difficult to find developers who have that mindset. Moving on to machine learning and AI. You might think that machine learning is the territory of a data scientist, but if artificial intelligence is the top of the pyramid of business needs, then the ability to collect and move data is a primary need for a business to get to the top of the pyramid. So data engineers are required here too. Last comes streaming and real-time data. With advancements in technology, more and more prediction is done in real time by deploying a model into the streaming pipeline and performing model scoring on every data point in that data stream. We also live increasingly in a world of real-time information and decision making. Building a streaming data pipeline rather than batch data pipelines is yet another new set of skills that data engineers must be able to implement. Here are 9 of the key data tools on Azure that a data engineer needs to know about. Azure Data Factory, Azure Databricks, Azure Stream Analytics, Azure Synapse Analytics, Azure Data Lake Storage, Azure SQL Database, Azure PostgreSQL Database, Azure MariaDB, and Microsoft Azure Cosmos DB. Let's take a look at the data pipeline and how it works and what you can expect to happen on every stage of the data pipeline. The first step is the ingestion. Here you get log files, media files, generally unstructured files, and you get a lot of information from business and custom applications. All of this goes into the Azure Data Factory. Now this is all being ingested and brought into Azure. After you have your data, you've ingested it, you need to store that data somewhere. So you can store that data in the Azure Data Lake Storage. From there, you can also use it immediately to model and serve. If you want to do that on raw data, then you can do that immediately from Azure Synapse Analytics and Azure Analysis Services. But right now, this data isn't processed. It's completely raw. So to process this data, we can prepare it and train it in Azure Databricks. From Azure Databricks, we can send it to Power BI to send business intelligence reports. and we can send it to Azure Cosmos DB for storage or to be displayed in web applications. This lesson is focused on using the term data workload in the sense of the purpose of the data. In this case, transactional versus analytics workloads. Transactional workloads typically operate over business data. Transactions are characterized by short, precise, and fast interactions which may involve one or more steps. Analytics workloads are known for operating over large, rich datasets that have a lot of historical data or fast-moving streaming data, unlike transactional workloads, which usually involve adds, edits, and deletes of data. The focus of analytics workloads is providing data in a form that can be queried. Those queries are optimized for business intelligence and decision support, as opposed to the more straightforward and simple queries of transactional workloads. Both types of workloads rely on industry data, which tends to be specific to a domain. For example, in the healthcare industry, there are special codes for diagnosis and then others for procedures performed by physicians. Those would fall into the category of industry data. Online transactional processing, or OLTP, is often used to describe transactional workloads. A really common example of OLTP is the transfer of funds from one bank account to another bank account. In this two-step interaction, it would be a very bad thing if only the withdrawal were conducted and the deposit into the destination account never happened. So that's wrapped in a transaction. If either the withdrawal or the deposit fail, then the entire transaction fails. Online analytics processing, or OLAP, is used to describe analytics workloads that are performed over large sets of data at rest. Then at the other end of the spectrum, you could have analytics workloads that run over real-time streaming data. HTAP, or Hybrid Transactional Analytic Processing, refers to scenarios that support both aspects of transactional workloads as well as analytic workloads over the same set of data. So what is a data warehouse? A data warehouse is a central repository of information that can be analyzed to make more informed decisions. Data flows into a data warehouse from transactional systems. Relational databases and other sources, typically on a regular cadence, business analysts, data engineers, data scientists, and decision makers access the data through business intelligence tools, SQL clients, and other analytics applications. Data and analytics have become indispensable to businesses to stay competitive. Business users rely on reports, dashboards, and analytic tools to extract insights from their data, monitor business performance, and support decision making. Data warehouses power these reports, dashboards, and analytics tools by storing data effectively to minimize the input and output of data and deliver query results quickly to hundreds and thousands of users concurrently. Data lakes are designed to capture raw data that can be in any form. They are made to handle large amounts of data and are commonly used for machine learning and artificial intelligence or for analytics with processing. Data lakes can be organized and put into databases or data warehouses. With the rise of integration between traditional data warehouses and data lakes happening with many customers, the concept of a lakehouse is starting to become more popular. A lakehouse is where you combine the traditional data warehouse approaches, analyze structured and semi-structured data, and combine it with the unstructured or semi-structured data stored in the data lake. For example, unstructured data could be things like images, texts, web pages, all of which need to come together and be understood from a holistic point of view. A lakehouse has the following key features. Transaction support. In an enterprise lakehouse, many data pipelines will often be reading and writing data concurrently. Support for ACID transactions ensures consistency as multiple parties concurrently read or write data, typically using SQL. Schema enforcement and governance. The lakehouse should have a way to support schema enforcement and evolution, supporting data warehouse schema architectures such as star and Snowflake schemas. BI support. Lakehouses enable BI tools directly on the source data. This reduces staleness and improves recency, reduces latency, and lowers the cost of having to operationalize two copies of the data in both a data lake and a warehouse. Storage is decoupled from compute. In practice, this means that storage and compute use separate clusters. Thus, these systems are able to scale to many more concurrent users and larger data sizes. Some modern data warehouses also have this property. Openness. The storage formats they use are open and standardized, such as Parquet, and they provide an API so a variety of tools and engines, including machine learning and Python or R libraries, can efficiently access the data directly. There is support for diverse data types ranging from unstructured to structured data. The Lakehouse can be used to store, refine, analyze, and access data types needed for many new data applications, including images, video, audio, and semi-structured data and text. There is support for diverse workloads, including data science, machine learning, and SQL and analytics. Multiple tools might be needed to support all these workloads, but they all rely on the same data repository. There is end-to-end streaming. Real-time reports are the norm in many enterprises. Support for streaming eliminates the need for separate systems dedicated to serving real-time data applications. Two examples of data lakehouses are Databricks and Azure Synapse Analytics. Let's look into these with a bit more detail. To give the reliability, robust governance, and performance of data warehouses with the openness, flexibility, and machine learning support of data lakes, the Databricks Lakehouse platform combines the best components of data lakes and data warehouses. By removing the data silos that normally separate and complicate data engineering, analytics, BI, data science, and machine learning, this unified approach streamlines your modern data stack. It is constructed using open standards and open source to increase flexibility. Additionally, its standardized approach to data management, security, and governance enables you to work more productively and develop more quickly. Azure Synapse Analytics is a limitless analytics service that brings together enterprise data warehousing and big data analytics. It gives you the freedom to query data on your terms using either serverless on-demand or provisioned resources at scale. Azure Synapse brings these two worlds together with a unified experience to ingest, prepare, manage, and serve data for immediate business intelligence and machine learning needs. We've talked about centralizing data in one location, which is copying over the data, whereas a data mesh concept is decentralizing it, meaning that you don't have to collect all of that data into one location. Let's understand what data mesh is with a bit more detail. Data mesh is a decentralized approach to data management that focuses on domain-driven design. It aims to bring data closer to business units or domains where people are responsible for generating, governing, and treating the data as a product. Data mesh has 5 important principles that you need to keep in mind. Domain-oriented decentralized data ownership and architecture, data as a product, self-serve data infrastructure as a platform, federated computational governance. Let's look into each of these with a bit more detail. In a data mesh, an individual domain takes full ownership of its data from end to end. It ensures that the data is trustworthy or is of high quality, and has a domain-specific context and is consumable by other domains within the organization. The second principle centers around treating data as a product rather than just as an asset in an organization. This works in conjunction with distributed domain ownership of data. Now that each domain owns its data and is responsible for producing and catering data to its consumers, it is expected to be high quality, fresh, and trustworthy. Data teams need a platform to build domain-specific data products and serve those data products across business units in a self-sufficient way. However, to allow domain teams, such as engineers, domain experts, and owners, to have a complete focus on developing quality data products, it is essential to abstract the infrastructure to facilitate self-service. The final data mesh principle aims to support all 3 principles discussed above by letting each domain exercise governance over the data products that they build locally. However, domains must still adhere to the standard rules that the organization has decided upon globally. This is important, particularly with a decentralized approach to run the ecosystem in harmony and achieve data interoperability. Ultimately, this model aims to have a strong collaboration between the local domain and the global governance team to cater to all the data needs. Some of the benefits of data mesh are as follows. You have easier and faster access to data. Data consumers have the data available to them, which reduces the time to insight and allows businesses to make faster decisions. You have flexibility and independence. It gives ownership and autonomy of data to teams that know the data best. It has standardized data observability by explicitly prioritizing treating data as a product, which helps to establish a data-driven culture. Lastly, you will find business agility and scalability. It reduces overhead on central data infrastructure teams, who can now focus solely on improving the platform. Data Fabric is a collection of practices and tools used to implement data connectivity across the entire company estate. On-premises systems, all cloud data storage services, hybrid storage systems, and even edge devices. Think of a data fabric solution as the nervous system in our bodies. Its purpose is to distribute various kinds of information to the organs, or the business systems in this case, requiring it for decision making. Data fabric is the complementary coding you can use to connect disparate data lake solutions with data warehouse tools to resolve interoperability issues, improve data distribution speed, and achieve better data standardization. Some data fabric solutions are SAP Data Intelligence, IBM's Data Fabric, and Google Cloud Dataplex. The benefits associated with Data Fabric are as follows. You have smart integration. The aim of Data Fabric is to unify data across different data types and endpoints using semantic knowledge graphs, metadata management, and even machine learning. This helps data management teams to cluster related datasets and also weave new data sources into the data ecosystems, so it helps eliminate silos across data systems and improve overall data quality. It provides data democracy. Self-service applications can be built using Data Fabric architectures. This allows data to be accessed by not only technical teams like data engineers, developers, and data analysts, cutting down on data bottlenecks. This means more productivity overall, thus becoming an enabler for better and faster decisions. You have better safeguarding of data and compliance. Increasing data access does not have to compromise data security. By putting more safeguards around access controls, it ensures that specific data is only available to certain roles. Using Data Fabric architectures cuts down on risks associated with data sharing. Data fabrics are becoming increasingly popular as businesses look for more ways to improve their data management and make better use of their data. Here are some use cases. You can improve data management. A data fabric can help you manage your data more effectively by providing a single unified view of all your data. This can help you identify and track data more easily and to make better use of your data overall. You can reduce costs. A data fabric can help you reduce the costs associated with data management by allowing you to consolidate your data into a single platform. This can save you both time and money. There is support for real-time data analysis. A data fabric can help you support real-time data analysis, which can help you make better decisions more quickly. You can scale your data operations. A data fabric can help you scale your data operations by allowing you to easily expand your data processing capabilities. Data visualization and analytics is turning all that processed data into neat and easy to understand graphs and tables so that trends can be understood and analyzed. Visualization is extremely important when it comes to making business decisions. Business analysts rely deeply on data visualizations. Visualization and analysis of data is only one end of the data pipeline. It can further lead into the decision-making process or even to train a machine learning model. We will look at some different kind of ways to view our data. First, we have bar graphs. Categorical data is shown using bar charts. Both vertical and horizontal bar charts are acceptable. Bar charts can be stacked or single-valued. Bar charts are excellent for use in dashboards and reporting. Now let's look at the time series graph. The sequence of the data points is based on time. Time series graphs are excellent for spotting and analyzing trends. For time series forecasting, time series graphs are also used. That is to say, for making future projections. Finally, we have scatter plots. Now, scatter plots are plotting points on the Cartesian plane. Scatter plots are typically based on two variables, that is the x value and the y value. However, you can include other variables, and this can be shown by the color of the points or by the size of the points. There are four aspects of data that we will be discussing: data movement, data ingestion, data storage, and data transformation. Data movement is the movement of data. Where is it coming from and where is it going? Data points being created somewhere and then they have to move, and when that data moves, we have to do something with that data. Data ingestion is what we call the process of moving our data into our data processing system. This data could come from anywhere and could be any shape, size, or form. At the end of its journey, the data is placed in either a data warehouse or a data lake, depending on the situation. Here we have our ingestion sources on the left, and this could be business applications, custom applications, and sensors and devices. and that data needs to be pulled into our cloud. Now to do that, we're going to have what's called an ingestion layer. The ingestion layer is where we take all of those different data sources. It could be a bunch of different cache registers. It could be, like I said, log files, whatever you want. And we're going to ingest that data into something like Azure Data Factory. Now we're going to talk a lot about these services later, so don't get bogged down by what Data Factory is. Just know that Azure Data Factory can be a fantastic ingestion source to pull data into the cloud. So we've moved it, but where are we moving it to? That's where our storage layer comes in. And we'll take something like Azure Data Lake Storage Gen 1, and we will move our data from Data Factory into the data lake. Now, once we have it in that data lake, we're going to have all kinds of different data in there, and it's not going to be particularly clean either. This is where data transformation comes in. You're going to have all sorts of differences between different data types. It could be duplicate data, it could be data that's misspelled, and when we try and use that data, it becomes very difficult with duplicates or missing data or misspelled data or different types. And so we do data transformation. So you could use a service like Azure Databricks or Azure Synapse Analytics to do data transformation. So we could pull data from that data lake and we could start to manipulate and work all of that data together so that it's all similar. This is data transformation, and you'll also hear it called like a cleaning step or a processing data layer. That's what we're talking about. We're talking about making all of the data the same so that it can be used for business decisions. That's data transformation in a nutshell. Let's take a look at what Azure has to offer and start with Azure Blob. This is a primary storage service in Azure that includes data lakes. Then we have Azure Data Factory, which is Azure's version of a managed pipeline. Then we come to Azure Synapse Analytics. If you deal in structured data, Azure Synapse Analytics is definitely the way to go. Moving on, we have Azure Stream Analytics, which is a service that provides streaming capability and light transformation. And then we have Databricks, which is a service that provides ETL analytics and machine learning at a massive scale.